All right, let's begin the next subject. We've finished with angular momentum last lecture. Today we're going to do just a sort of a side note. So I don't have time to get too much into this subject. We're going to cover fluids. What is a fluid? Fluid is a fluid. A fluid is sort of a broad term, a broad statement. There are many types of many states of matter. There is a solid, fluid, or liquid, and gas. There's also plasma, and I believe there's a fifth one is Bose-Einstein condensate. For this sort of general term, fluid, you can think of it as kind of a little bit of mixing liquid and gas, just things that may be able to move around one another. Or I should say individual molecules. So consider a fluid as something that is made of many tiny microscopic pieces, or in the case of how we may know it's many thousands of molecules that all interact with one another in a regular fashion. It's different than a solid. A solid has a rigid structure. Then we've been doing most of our calculations for solids up to this point. We've had a solid point mass. We've had projectiles is just a single object. We just considered a single spot that we've calculated the trajectory for. And even for something that rotates, like a spinning disk or a spinning cylinder, it's just an object that doesn't change its shape. This is a solid. Let me get a better color than this. So actually, let me go. That's okay. So if we sort of zoom in on the structure of this solid here. So I'm going to just imagine I take this little slice and I zoom in. Let's try to make this decent looking. Okay. If I just get a microscope, I'm going to zoom in. This solid is arranged of molecules that are in a very uniform fashion. So since this is the edge, there is a very definite edge to this structure. And all of the space within this solid is made up of individual molecules, but they're all bound together. They all act as one. See, they are all, if I had enough room, I'd make them all look like they're all linked like that. I don't have enough time to sort of link all of them. I'm just going to do like that. And it depends on the actual chemical structure on how the material is linked together. I just made them general circles in this case. If we look at a, actually, let me write that down. So each molecule is locked in place. And this is the reason in all of our calculations up to this point, we didn't have to find out the speed or the trajectory of maybe like a cannonball. Now, if we didn't have to find the trajectory of that molecule, and we didn't have to find a trajectory of that molecule, or maybe even that one also. We didn't have to find all of these individual little pieces, since we just were able to say they're all moving the same way. Inside of a fluid, take a similar sort of sample of it, zoom in, this is where we see that all of these bonds have been broken in some way, and all of these individual tiny little particles or molecules are free to move how they wish. So I'm just going to represent that by having them spaced out randomly. And technically they should all be sort of pushing on each other, since gravity's pushing them all down. I'm just giving them a bit of space to show, to represent the. And they all might have their own different velocities in different directions. Now you can see that I would have to consider that each and every individual molecule, since each molecule, I'm gonna put this underneath also. Each molecule is free to have its own motion. This becomes a big headache if we wanted to try to maybe have a fluid or some kind of liquid as a projectile. Imagine if we tried to take a ball of water and fling it somewhere. Is it going to remain as a ball when it reaches the target? Probably not. It's going to, deform, become, spread out, all of that. Sort of what we can expect from throwing a liquid or a fluid. This is where we need to define some things to make working with a fluid easier. So we're going to define density. For many of our calculations, it's important to know how an object moves. That's the purpose of this class in general, is the physics of how things move. Describing how things move. This is kinematics. That's the whole meat of what we're trying to solve for. If we can't figure out how a fluid may move, well, then we're going to have to find a way to describe it. Using density of a fluid, say instead of looking at this sample here, I took a small little, sliver of it. If I take that small sliver and, right, so go like that. So it would take a long time to count every single molecule in this entire glass of liquid or fluid. So what we're going to do is we're going to take that small sliver and we're going to find out within this certain volume, what is the amount of mass of each of these particles. You see, counting all of this would be a headache, but counting all of these in this picture, that's a little easier. There's about, 7 or 8 of these individual molecules. So what we're going to do is take this average. And this average is a ratio of how much mass is all of these, added up all of these individual particles or molecules, and how much space does it take up? How much volume does it take up? So this is what is known as density. Density, the formula is, it looks like lowercase p. This is a Greek symbol, rho. So rho is mass over volume. I could do this for the fluid in this glass up here. I could also do density of a solid. That's also true. I could take a sliver of it and find out what the density is of a solid. And the thing with density is people have already done many and many repetitions of this and have found out that certain molecules and certain arrangements have a set density. There is a set density for water. There is a set density for all of the elements on the periodic table. They take up so much space and they have a specific unit of mass. So it makes sense that they all have their own individual and different densities. And I could also put for this, before I change screens, it's this small, it's the small individual slices of mass over the small changes in volume. Right, so for density, I can look up any material I want, and someone has probably already measured it and cataloged it. Does that mean I'll always have density for a problem? Maybe not. Maybe I want to find the density of a unknown object. Well, this object has, it's a very odd looking rock or something. I don't know what the density is. Maybe it's gold. Maybe this has a lot of gold in there. So what I would have to do is figure out how much mass there is. And I could do this with the entire solid object. I could find out the entire mass of this object, and I could find out how much volume it takes. The ratio will give me the density. All right. Moving on to pressure. Like this. There we go. Pressure in a fluid. So when a fluid, this free moving molecules, particles moving past each other, when they come into contact with a surface, they're going to be pushing on the surface. Let me get that picture in here. So we have this glass of water here, or a glass of some fluid. And instead of drawing, I could draw a little bit. Instead of drawing, all of these, hundreds of thousands of individual particles in here, what I'm going to do is, let's do another sort of slice. So here, let's look at what's happening inside of this small area. So we have the wall of the glass. So that's going to be this. So this is a solid structure. And all of the individual molecules of this fluid are, in some way, they're pushing on this surface. So again, they would be a little more tightly packed than how I'm going to draw it right now. But this is just for representation. So they're all moving with their own directions. See, that one's moving like down. And they're all bouncing off of the glass here. And since they're all pushing on each other and they're all pushing out on the glass, there is this net force normal to the surface of the glass here. Let me like that and like that. And the equation for pressure is force per unit area. Okay. But that's not the whole picture. Let me maybe add a few more of these arrows in here. The water or fluid molecules that are on the top here. So imagine I take a little slice like that. I'm just looking at the top layer. They're pushing out on the sides of the glass. That's perfectly fine. But then the ones, if I take another slice, another layer down, like that, the molecules in this region are pushing out on the sides of glass, but they're also being pushed down on, they're sort of being sandwiched by the molecules on the top. So they're having this greater force outward. They're sort of being squeezed out to the sides. So there's this greater pressure out on the sides like that. And this pressure increases the more you go down on into this sort of a tube or glass of water. You may have experienced this when swimming in a swimming pool. There's a large pressure down near the bottom because you have, as you are sort of swimming at the bottom of a pool, you have this column of water resting on top of you. This, hundreds of thousands of molecules of water sitting on top of you, all the way up to the surface of the pool. All of this mass is creating this, increased pressure and increased force. So the force itself would increase, so the pressure increases. Okay. And I'm just going to put this in here for later. H naught. So it depends on the height of this column of water. And these arrows, they're representing, or I'll put that right here. I'll say force normal to the surface. All right. Something else that might be helpful is using the density formula we've just arrived at earlier. If we know the density of this fluid, maybe that can help us out later on when we need to figure out the pressure, and it's not necessarily water. It's not, we don't know how much mass. So say if I went and swimming in a pool of olive oil or, some sort of other liquid, I don't know how far down I could get before I reach a certain pressure, how much mass, all of these individual molecules would be resting on top of me. It'd be important to know how the pressure may change in different materials. So let me clarify. This is a capital P. Capital P, and I'll try to make the rho for density look a little different. So I'll say also helpful. We take that force, mg, and we insert the equation for density we've just arrived at, and we solve for mass. So that will be rho times volume times gravity, acceleration of gravity. And this becomes, so I'm going to take this, and it will become rho times the area of sort of the cross-sectional area of whatever is under the water times the change in height. So this is how we could factor in how far down something might, the pressures involved in going deeper into a fluid. So we have this change in height. Where did I get this from? This is area times height. That is volume. That is volume. All right. Something that we can use this with, let's do a little side example. Relating pressures is some sort of lift, some sort of hydraulic lift. A lot of fluids, water is water, namely, is incompressible. So you can have a solid box of water and try to squeeze it, or squeeze its structure together. It will not sort of bounce or have any sort of elasticity to it. Water is incompressible. We could use this to our advantage in a system like this. if we have this hydraulic lift and we apply a force to a piston, so imagine this is all water or some sort of incompressible fluid, and we have these plungers here, and here. As I push one plunger down, the other plunger, so as I push one down, the material in here cannot sort of be squeezed at all, so it's going to push this other plunger up. So if I apply a force, we'll call it force 1, to this small plunger down here, and it has a specific area. Imagine this is maybe a disc that I'm pushing down. Here, it's an area we'll call A1. What would be the force of that second plunger being pushed upwards? And it will also have its own different area. It's much larger. Well, we know that's the first sort of section of it. And for this, let me just say beforehand, for the problem, we're ignoring just most of this part. We're only concentrating on what's happening to the plungers themselves. Now for that first section, for that first plunger, F1 over A1, and the second plunger equals F2 over A2. The pressure in the system, since this is an incompressible fluid, then I'll say pressure is constant, so we can do this. So I'll say P1 equals P2, which means we can use the relation F1 over A1 equals F2 over A2. Ultimately, we can solve for that second force. Now, before I do an actual example with values, you could see here, looking at just this equation I've written down, let me rewrite that. What is A2? That's the size, or that's the area of that second plunger. Is it bigger or smaller than A1? So A2 is bigger than A1. Okay, so that's a larger value on the top, small value on the bottom. So this will be a value greater than 1, which means that there's going to be a larger force applied upward here. So I can apply a small force. F1 can be small. I could apply a very small force downward on this side, and it will turn into a very large force upwards on the other side. Hopefully we can see that. Let's move to this example. It's going over the same exact sort of problem. Okay. We have a large piston of a hydraulic lift. There's a radius of 20 centimeters. What force must be applied to the small piston of a radius 2 centimeters to raise a car of mass 1,500 kilograms? All right, so I'm going to try to keep that picture up in the top. So for the first one, we know F1 is pressure times A1. Since this is a hydraulic lift, we don't know if the exact fluid they're using. We can just assume it's incompressible. One, and let's do F2, E2, and we can just say that we do need to know F2, A2. Yeah, there we go. I made that. Yeah, that's what. There you go. A2. Let's take this first one. Let's take this first equation here. And the second part of the first equation, let's solve for the pressure. Pressure is F over A2 and that is just the mass of the that. All right, so in this problem, we're solving for F1. That's going to be that's the final result. M G. This is the this is the mass we're wanting to lift for A2. All right, we have the pressure. The pressure is constant for both of them. So I could take this pressure I've just found and put it into that first part. One is the A1, and that is just mg over A1. Oops, sorry, A2 times A1. Mg, and it turns into just a ratio of A1 over A2. So I'm really just combining these two together in the parentheses. We have mg. What's the area of, again, it says that this piston has a radius. So I'm assuming it's a perfect circle. The area of a circle is pi r squared. Pi r1 for that first one squared over pi r2 for that second one squared. Pi's themselves cancel. We have now 1,500 kilograms times 9.81. We'll use the units newtons per kilogram. So they'll cancel out some kilogram units. And we don't necessarily have to convert to meters for this segment because they will cancel out right here. Doing this calculation, we get that F1 the force we would have to apply on the small cylinder would be 147 newtons, or just approximately 150 newtons. All right, so the force we apply to this small cylinder, since there's this transfer of forces from a large piston onto a small piston, means that we can use a smaller force to lift a larger object. So let me real quick, 1,500 kilograms times. All right, so it's averaging that the force of that car by itself, the force of the car by itself, I'm going to erase this in a bit, force of the car due to gravity is about 15,000 newtons. That's how much the car weighs. And so in order to lift it, I'm reducing this by a great margin just by using this hydraulic advantage, using this hydraulic lift. All right. Next up, we have buoyancy and Archimedes Principle. This is where we can sort of take a step back and ask maybe some more basic questions with fluids. Like, why does maybe like a piece of wood float in some water? Why does a stone sink in water? Why do things float and sink? You might say, well, wood, it's maybe a little, it's lighter, it's relatively light, maybe porous, it's lighter or less dense than water. And a stone, well, it's compacted, it's dense, it's more dense than water. The answer is a bit more sort of subtle than just saying being more or less dense than water. So on a technical note, for these these two scenarios, that may be true. The wood may be less dense than water. But what if there's let's do a more tricky example. What about like a ship on the ocean? What are ships made out of? Ships are made out of metal. Metal is very, very dense, much more dense than water. Why don't they sink? Or when they're operating normally, why don't they sink? They could even be carrying a large amount of cargo. They still manage to stay afloat and go from one place to another perfectly fine. The reason for this, this is where we see that we have to step back from it saying it's just the object's more or less dense than water. We need to use Archimedes' principle. So the answer lies with the Archimedes principle. What it's saying is a body of wholly or partially submerged in a fluid is buoyed up by a force equal to the weight of the displaced fluid. What this is saying in simple, sort of straightforward terms is that the buoyant force, so let me write that down here. So buoyant force, I'm going to use for my notes, I'm going to say F sub B for buoyant force is equal to the weight of the displaced fluid. So the buoyant force, we've all maybe experienced this when swimming. There's just this general force upward when we're diving underwater. We might stop swimming for a minute and we have this sort of upward motion. We start to rise once we're underwater. This is the buoyant force. It's forcing us upward. All objects, when they're in some fluid, experience a buoyant force. Let's take a look at it a bit more closely. So say we have an object, it's just a mass. Let's say it's a block of metal right here. And I'm just letting it fall into this glass of water, this container of water. The initial height of the water is right here. So initially, the volume of water is right here. And this object itself has a force downward, a force due to gravity of this block. I'm just going to say Fg of the block. All right. Once the block is placed into the water and starts to be submerged a bit, let's take a snapshot right at this moment. It's still experiencing the same exact force downward due to gravity. So G of the block. Also, same exact thing. That doesn't change. But this is where, with this block or with a swimmer in a swimming pool, there is a buoyant force upward. Make this a bit larger. All right. And how much buoyant force there is depends on the volume of displaced water. So initially, the water volume was right here, where this dotted line is. That, let me go like that. I'll just say this is the volume of displaced water. And once I place an object in and it is completely submerged in a fluid, the amount that the water rises, so this amount that the water rises is the exact same. And I'll put this down here also. So since submerged, is the same as the volume of the object. So if I was to measure the volume of the block itself, it would say it would be V VB for block. And then if I were to measure the difference here, that would turn out to also be VB. It's a relation, direct relation, since this block is completely submerged. You could think of it as I've inserted a block of material where there was once just water, and that water has to go somewhere. And it's an equal volume of water that is pushed out of the way. So it's an equal block of water that is pushed out of the way. However, once this water is pushed out of the way, it has to create room for it somewhere. Go down like this. Okay. This water itself will have its own force downward. Let me try to go like that. Okay. If G of the displaced water is the mass of the water that was displaced, and this is the weight of the displaced fluid. And so this weight right here, this weight becomes the buoyant force. So this, that makes this equal to F sub B. All right, maybe we have a scale underwater that we're doing some measurements with. And we take a measurement of the weight of a block in air, and we take the weight of a block underwater. Will they be different? Well, we would have to sum up the forces in this case. In air, there's only one force downward. In water, there is the force downward, but then we have to subtract out that little bit of force pushing up. So there will be a different reading on this scale if we were to do this experiment. So I'll say the apparent weight and I'll just say F apparent of the object becomes and we'll so summing up these forces in this picture, and for this picture exactly, I would have this be block. I want to keep it general, so you can use that equation for a different problem. All right, so we'll do a little example of this. Let's say one quick thing while I'm still on this picture. One thing is, why upward? Why are things not just forced downward? Like what I was saying earlier with the difference of pressures. So there's a small pressure, the pressure increases on the side of the wall of a container. Now imagine the pressure on the sides of this object that's underwater. So there's a small amount pushing on the sides this way, and then a slightly larger amount in the middle, and a very large amount on the bottom. Now look at the difference between them. They're in opposite directions, so they cancel out left and right. That's why when you go underwater, you don't just move to one side, but there's this gradient. There's a small amount that cancels that way. That one cancels that one. That one. But since there is a larger pressure on the bottom, it is forcing up to the lower pressure region. I think I'll leave those arrows in the picture. Okay. This is also why balloons float upwards. A balloon is filled with a gas, and gas is just a more excited liquid. We could just, in general, encompass this in the term fluid. So this gas inside of this balloon is displacing a lot of air around it, and the gas inside is less dense. It's displacing a very heavy amount of air, a large weight of air. So there's this pressure difference along the shape of the balloon. So it floats upwards to a lower pressure region. There is a point where the pressure on the outside of the balloon, so the balloon floats up and up and up, and the pressure of air decreases as you increase in altitude. There is a region where the pressure on the outside from the air molecules is the same as the pressure pushing out of the balloon, and so the balloon will just start staying stationary in the air. This happens for all types of fluids. It's just a bit easier to imagine with like a balloon in the air. All right. Now to the actual example. Okay, and you want to check that you want to check to see if a solid gold ring you found is real gold. So you weigh the ring on a scale and get a weight of 0.158 newtons. Using a string, you hang the ring from a scale and submerge it in water. The new weight is 0.150 newtons. Is this ring pure gold? And I've added a little thing here so you wouldn't have to look it up. In general, when compared to water, the density of water, gold has a ratio of being 19.3 times more dense than water. All right, so let's start out with listing what we know. Well, let me list things out first. So we have of G. This is the density of the ring by itself, the amount of volume it takes up times gravity. The same form, except for the buoyant force is the density of the water that is pushed out of the way, the volume of the water pushed out of the way or displaced, times gravity. Now let me draw a picture. I should draw the picture first, but here we go. Again, imagine that's our ring. And it's in the air, sitting on a scale. Doesn't have to be perfect. G while in air. Sure. Next up, we have the we measure the force or its weight in air, and then we measure its weight while in water. So this will be the apparent weight. So there's that scale again. We hang it from a string. And it has a new, let's go with that, FG, submerged. Sure. While it's submerged, I know that since it's being held in the water and it's being, it's motionless, that is practically just the tension in the string. That's the reading that we get. That's all. Fine, that's the apparent weight. Apparent. But remember what else was acting on something that's submerged in water or a fluid? We have a buoyant force somewhere acting on this object. So I'll say it FB is right there. It's a small amount pushing upward. And these two forces are canceling each other out, or trying to. And the result of this is what we see here, the apparent force. All right. So we have Fg is the density of the ring. And I really want to, since the problem has set me up, we want to maybe find the density of the gold, or since I've added this side note here, we want to find a ratio of gold to water. So the ratio of the density of gold versus the density of water. So that's why I'm going to be arranging it like this. Oop. Let's go like this. Density of water. EG, like that. Okay. Since it's pushing out the same, since it's displacing its own volume of water, the volume here will be the same, and gravity is the same for both. Those two terms cancel out. So we do get just a ratio of the density of the ring over the density of just water. Next up, we need to factor in this apparent force felt by the scale once it's submerged. So F apparent is equal to Fg minus Fb. So the mass while it was in air, or I'm sorry, the force, the weight of it in air minus its buoyant force. That means we can solve for that buoyant force. I'll just say app for apparent. All right. And this is good because buoyant force was related to the weight of the fluid displaced. And we don't quite know the volume of the ring or the volume of the water that was displaced. So it's good to solve for this so we don't have to actually calculate FB directly. We're going to use the two values that we do know. We know its weight in air, and we know its weight while it was submerged. So let's take this, plug it in right here. So we have Fg over Fg minus F apparent. Okay. This becomes, I'm just going to be doing left side. These are all values we know at this point. Newtons over, that's 0.158 newtons minus its apparent weight. There we go. So we have a ratio right here. We have density of the ring over the density of water is equal to 19.3 newtons, or sorry, the newtons themselves cancel. Around about 20. Okay. So this ratio is 19.3, just about equal to 20. So with the test we have done, we could say the ring is most likely pure gold. All right. So that's using the buoyant force to calculate for a ratio of densities. Let's let me do real quick. I'm gonna do a little practical example of buoyant force. So I don't have this next page prepared. We're gonna try. Actually, we'll just go like this. So for going back to that original picture. Yeah, we'll go back to that picture. Going back to the ship in the ocean, why does it float when it's made out of metal? Let's look at a example I have somewhat prepared here. It depends on the amount of water that's displaced. Go like that. All right. So I have a glass of water and a cup. If I place the cup in the water, it does not displace that much fluid, but the fluid that it does displace is its own weight. Okay. Now what if I instead add something like a quarter? I know a quarter will sink in water because a quarter has a very small volume for its mass. In other words, it has a high density. So the density of the metal in this quarter is greater than the density of water, so it will sink. So it just doesn't have that much volume to push water out of the way. What if I have maybe a container? If I have a large container like this cup, I could take that same mass and now it is being held inside of that new volume that can push the water out of the way. So now it is pushing its own weight of that quarter. I can do many other coins. Do something very severe. We're going to go like this. So instead of just a single quarter, just a lot of loose change. They are very dense objects, but themselves, they can't push a lot of water out of the way. They don't have that much volume. Placing them inside of a cup or some sort of container, they can displace a lot more fluid since they're being held or spread out. So we're going to have this initial volume. Let's hold it like that so you can see that. The initial volume. The water level rises a whole lot more since it is displacing a lot more water. And it's displacing an equal amount to the amount of to the weight inside of this boat or this container. I could add a little bit more. And it continues to float. But the water level keeps rising. So there is a limit for like a ship in the ocean. It can't hold infinite amount of objects in it because the water level can only be displaced by the volume of a ship. And if you know about sort of how the ship is made, there's a lot of, so the bottom of a ship kind of looks like this. And it comes out and up, similar to what the cup looks like, just a little bit pointier on the bottom. So this big metal ship is just pushing away a lot of water. But it doesn't have this large infinite volume, so it can't, hold things. It can't hold unlimited amount of things. Eventually, you can overload a ship. But hopefully that makes it a bit more clear on how something like a ship in the ocean or maybe even a piece of wood floats. If you think about it, maybe even a big, large, heavy a log in the river, how that floats. It's displacing a lot of fluid. It's displacing its own weight in fluid. Whereas a dense object by itself can't displace that much fluid. So it will sink. All right. So that's pretty much the chapter on fluids. I don't want to go in too much detail with fluids. There's, fluids in motion. That's a big mess. I don't want to do right now. We're going to start tomorrow on beginning some simple harmonic oscillations and looking at how waves might work. All right, so we're wrapping up the end of the semester. So I hope everyone has a good rest of your day. I will see you all later.